Hello. This video is on problem 3. Hold on, let me get my earphone on. Alright. So this question is a little bit messy, and to be honest, I'm not good at explaining this question. So if you guys could just leave the comments below and you think you can explain better than I do, go ahead. By all means, I'm always welcome with I welcome other comments. But anyway, now, so this question is difficult because it's given a freezing point, and you don't even know where the hell to start. So that's the answer in the book, but I got relatively close to that, sort of ish. It's just probably a rounding error, but if you guys would check that for me as we go through this question. So basically, if you don't know where to start, we always start with a skid chart, right? So we write it down what we know, and we know that, assume that molality equals molality. So we just assume that also equals to 1 mole per liter. So anyway, we start with 1, and change is negative x, and 1 minus x is your equilibrium. Same with that one and that one. Make sure everything's balanced. Yep. So x, right? Now, since we're given a freezing point, we could find the percent dissociation by looking for Van Hoff factor. It's because we're not really given the we're not given x, and we're not really given Ka. We have to find Ka, obviously. So we can actually use the relationship between your conjugated base and your acid. Since we know that anything with COH, carboxylic acid, they don't dissociate completely. So we can actually look for the percent dissociation from here to here. So which would be x over 1 minus x, right? And we equals to some kind of percentage, right? Now, after we look for that, right, so we can look for I, and so your Van Hoff factor would be 1.037634409. This means that instead of I equals 2, it dissociate less than I equals 2. And to be honest, like, the percent dissociate, you just have to find it through it's just 1 minus I. But to be honest, I looked it up and I don't really know how to explain that. But I think if you don't really want to know why, just know that when you find I, you just have to take 1 minus I to give you the fractional percent. No, not a percent. Fractional whatever. So it's going to give you 0.037634409, and in times 100% means, and you get 3.764%, means that from your conjugated base over your conjugated acid is dissociated just 3.764%. So which is a little bit, it makes sense because it's carboxylic acid. It doesn't dissociate that much, so we only expect it to be very little. So anyway, so we know that the relationship between those two is that. Okay, so as we go down here, we know Ka is your H3. It's H equals to H3O plus times your conjugated base over your acid. Okay, so now we know these, when your conjugated base divided by your acid is 0.03764, but we don't know the concentration of H3O plus. So we just go back to find it. So we know that x over 1 minus x, which is your conjugated base over your conjugated acid, equals 0.0376344. Yeah. And then you just find x. You can get 0.036264422. And then you just plug it in, and you get Ka equals 1.39-ish, and times 10 to the negative 3, and just round it out to 1.4 times 10 to the negative 3. Although it's sort of like far away from that, just a little bit, but I guess it's close enough. But I'm pretty sure I just round like just rounding error somewhere. So if you guys would check that for me, or I did something wrong, just feel free to tell me. And that's it for number 3. I feel so awkward. I need to be less awkward.